The climate in the Arctic affects the climate outside of the Arctic.
The Arctic is warming at twice the rate of the temperate areas of our planet.
When I started my career in the Arctic in 1981, 85% of the Arctic basin was covered with multi-year sea ice, which is this stuff that survives the summer and grows the next year. It's very thick and hard. Well, now only about 12% of it is multi-year sea ice.
The thick multi-year sea ice has now transitioned to thinner first-year ice. So it's gone from like 10 feet to 2 or 3 feet, and is much more mobile.
The sea ice dynamics in themselves have impacts that go far beyond just the ocean, so to say, where the sea ice is.
There are signs of a connection between the Arctic and the rest of the world.
Those connections, teleconnections, as they are sometimes called, should be studied further.
There's what we would call an emerging signal, an association between the loss of sea ice and the warming of the Arctic and the frequency of severe weather events, especially during the winter season in mid-latitudes, in particular eastern North America and eastern Asia.
You have this big heating in the Arctic area.
And that causes the polar vortex, which is a byproduct of the high pressure pattern over top of the pole. It's causing that to break down because you've got a lot more heat coming from the ocean up into the atmosphere.
That essentially changes like the jet stream. It causes the jet stream to kind of do dips farther down.
The polar vortex is the jet stream.
Whenever you see big storms coming or heat waves, if you look at the jet stream, you'll see these big dips.
What happens basically with the polar vortex is you get a lot more lobed structure to it, and those lobes penetrate down far over top of the planet towards more temperate latitudes. If you're on the outside of one of those lobes, there's a tendency to draw up warm air much further into the Arctic than you would have otherwise. And if you're on one of the cold sides, you'll draw down cold air down into that lobe on the other side.
And so you get more extreme heat waves, more extreme storms, more extreme cold.
So people in, the southern states, for instance, will go, man, I'm in southern Florida and it's like freezing cold here in February. It's supposed to be warmer than this. Well, you're sitting underneath that lobe that is drawing that cold air down from the planet. Some people will be sitting up in Alaska at the same time and say, wow, it's way warmer up here than it used to be. And it's because that warm air is penetrating much further north.
So there's lots of evidence that the loss of ice north of western Russia blocks the jet stream and allows colder air to reach into eastern Asia.
A similar thing happens in the eastern United States in the sense that the sea ice loss north of Alaska is fairly pronounced, especially in the summer and autumn. That tends to build up this upper air ridge in the early part of the winter, even into midwinter, and that in turn leads to a downstream impact, which is the northwest to southeast flow that reaches the Midwest and the eastern third of the U.S.
Multi-year ice, because it is a more stable and a more long-term environment in the Arctic ecosystem, is believed to host more of the biodiversity. It acts as a repository or a storage for biodiversity.
We're finding species that we would have historically thought to be what are called boreal species. So these are ones that are a little bit further south of the Arctic, the true Arctic species. People in the scientific literature have coined this the Atlantification of the Arctic on the Atlantic side and the Pacification of the Arctic on the Pacific side.
Some of these new species, the winners, include large marine mammals such as the killer whales, which are expanding their range to the Arctic, taking advantage of those new open water areas to basically compete with the polar bears as a top predator.
What we see in the Canadian high Arctic over the last 5 to 10 years is very strong warming in the summer, which has led to dramatic increase in melt rates. That means that areas that weren't melting 10 years ago now do melt, and that extends pretty much to the highest elevations on the ice cap.
So here we are at one of these holes where the massive volume of meltwater drains into the ice sheet. There's thousands of these things all over Greenland. The water drains in to the bed, it lubricates flow and accelerates the motion of the ice toward the sea.
The melt rate is now about twice as high in summer as it was 20 years ago, which is quite a significant increase over a short time.
In the coming century, Arctic land ice is contributing about half of the global sea level rise.
We will continue to see overall ice loss from the Greenland ice sheet, at least for the next 100 or so years.
The current best estimate for global sea level rise at the year 2100 is either about half a meter or 75 centimeters, and the difference depends on which policies that the globe chooses.
Our questions now are, how quickly is sea level rise going to happen? Where is that ice going to be coming from? And how quickly are we going to lose it?
But I want to stress that those numbers are probably underestimates, because the projections, they haven't yet put in all of these sensitivities that we're finding in the SWIPA reports. We've been surprised that meltwater lubricates the whole Greenland ice sheet. We've been surprised that ocean warming is destabilizing glaciers. We've been surprised that biological darkening is happening. All of these other sensitivities we didn't have in our minds before, and they're adding up and multiplying each other. There is still a lot that we don't know about water movement through land ice, water storage at the bed. In the mid-90s, the conventional thought was the bed is frozen. There's no liquid water storage, and the last 2 decades have revealed there are subglacial lakes, there is liquid water perennially stored in the snow, there's liquid water stored at the bed.
We see that permafrost is continuing to warm, and warming was at a high rate. It's happening not only in Alaska, it's happening all over the northern hemisphere. Most of the location is still in the future, but according to our measurements, this future can actually happen much sooner than we were expecting, say, 10 or 15 years ago. So we may start to see widespread degradation of permafrost in discontinuous permafrost, like in interior Alaska, central Siberia, somewhere in a time scale of 20 to 30 years.
Permafrost thaw, it's something that can happen quite rapidly, but it will take a long time for the permafrost to regenerate. We will see release of carbon that is stored in the permafrost, and regaining that carbon, or sort of getting that carbon back into the storage is something that will take millennia.
For local and regional, thawing of permafrost means impact on infrastructure.
Many buildings and infrastructures were built taking into account melting, but not to such extent. And now it's melting, and just we saw a lot of pictures of destroying buildings, infrastructure, roads, especially roads.
Houses, roads, airports, all this already affected by thawing permafrost, and it will be much more affected in the near future.
So we see a change in weather patterns, we see a change in the ecosystems, the tree line has moved. We also see that there are new diseases coming into the reindeers. The Sami people has lived through a lot of changes in the history as well. So I hope that we will also adapt to the new changes that are coming.
By the end of the century, the changes due to permafrost thaw and the loss of the snow and ice cover will amount to several tens of trillions of dollars in economic costs.
Research is about trying to understand what we don't understand, and we still are a long ways from understanding some of these processes, but we're making good progress, and SWIPA helps us understand that at a more global context.
The main message that's coming through in this report, the main message we'd like to convey, is that over the time scale of the next 50 to 100 years, human actions can make a difference in the trajectory of the Arctic climate system. The way the cryosphere, ice and snow, will respond to climate change will depend a lot on the emission scenarios, which basically are determined by human actions.